Hello everyone, today we'll be going into the first and final episode of the Kinetics unit for our chemistry series on Stanton 101. It's Elijah, your chemistry tutor, and let's get into this. So, just as a brief outline, we'll be going over in this particular lesson problems dealing with finding the rate law and the rate constant, and problems dealing with integrated rate laws. Okay, so now let's get into a problem dealing with finding the rate laws and the rate constant. So this chart may look a little bit strange, but it is how it would look if you're trying to find the rate laws, because the rate laws and the orders right here, they must be determined experimentally. Now if we see this chart, it shows 3 runs in an experiment, like how you'd write down in a notebook if you're doing it for the science fair or some other sort of research. And you can see run 1 has its own value of A in the reaction and its molarity, and B also has that. It has the molarity, and then the rate of the reaction is given in molarity over seconds in the furthest right column, with values going from 1.22 times 10 to the negative 6 molarity over seconds all the way up to 1.41 times 10 to the negative 5 molarity over seconds. Now how you start out one of these problems is you need to be able to select 2 runs that cancel each other out, but do not cancel out a different reactant in the problem. So take for example, I chose run 3 here, and I did run 3 over run 2, and so that was this value, the rate value, over the rate value for run 2, run 3 over run 2. Same here, the run 3 values, the A goes here on the left, and the B here goes on the right, as you can see. And then on the bottom is our run 2 values, which is the same way. A is on the left, B is on the right, and it matches up fine here. So then you cancel these out. You cancel out the 2 A values, and therefore canceling out this X value right here. So let's cancel that out, put an X over the X. So then what you get is about 3, and then exactly 3 on the right side. So 3 is equal to 3 to the Y. Now we could just look at this and say, oh, of course, Y is 1, but what my chemistry told me, or my chemistry teacher, what he told me to do, or told my class to do, was to find it the proper way, which is log of 3 equals log of 3 to the Y, then log of 3 to the Y is equal to Y times log 3. Now with this next part right here, we're doing essentially the same thing, except this time we are canceling out Y to find X. Now let's look at these runs and do the same thing. So these 2 cancel out, and we'll be left with these being over each other. Now what we have here is what I just said. We have reactant B canceling out, therefore canceling out Y. Now let's put an X over the Y. And then you figure out X, and you do the same with the rates values. It makes 4. 2 to the X, or about 2 to the X, is equal to about 4. So then you do log of 4, log of 2 to the X makes X times log of 2. Then divide log of 4 by log of 2, and X is equal to 2. Now once you have your order values, you're going to want to write out the rate law again, which is K times A to the 2 times B to the 1, or that's at least how you would pronounce it in mathematical terms. So you would do now is select a random run. I chose run number 1, and if you scroll up to our little chart here, run 1 is in fact 1.22 times 10 to the negative 6, and then so since it's molarity over seconds, it's 1.22 times 10 to the negative 6 molarity over seconds equals K, and then you put in the values of molarity for that run, which were 0.22 and 0.15 respectively. Let's make sure that's correct. It is. Then here you make sure to use the orders that you found by doing what I showed you above. So it was 0.22 molarity to the second power, then 0.15 molarity to the first power. So then when you square 0.22 m to the second power, you get 0.0484 molarity squared, or to the second power, times 0.15 molarity, and that's no need writing a 1 there, just you don't need to write it. So then you multiply these again, you get 0.00726 molarity cubed, or to the third power, and then right here is where you divide it from this. I'm sorry I wrote it this way, but I just didn't want to write this a bunch of times. So you divide this right here by this right here to get K. So I did this and I wrote it out like this in a dimensional analysis type of way because we need to find specific units, and this is very important. So it'll be 1.22 times 10 to the negative 6 molarity over seconds times 1 over 0.00726 molarity to the third power, or cubed, whatever you'd like to say, and that's equal to K. So when you multiply, your units will be 1 over S, so it'll be S to the negative first power, and M over, or sorry, not M, molarity over molarity to the third power. So that'll make it molarity to the negative 2, I guess. And then when you divide the actual numbers, it gives you 1.68 times 10 to the negative 4. So your final answer here will be K equals 1.68 times 10 to the negative 4 molarity to the negative 2 seconds to the negative 1, or a better way to think about it would be, for your units of course, 1 over molarity squared times seconds. So this will be your rate constant, and these will be your exponents when you write out the rate law. So now that we're done with that, we can now do integrated rate laws. Now for integrated rate laws, there are different equations for different types of problems, and there are different hallmarks of what type of equation you'll be using. For example, with zeroth order, or as I like to call it, zero order, because I hate saying the word zeroth, for zero order kinetic rate laws, I guess, you'll be seeing this, m times s to the negative first power, or m over s, as your unit for k. And then here you'll have a equals negative k times time plus a sub 0. For first order, it's s to the negative 1, or 1 over s. This one's a bit more complicated because it's the natural log of a equals the negative k, or negative rate law constant that we just worked on in the other problem, times time plus the natural log of a sub 0. Then for second order, it's m to the negative 1 times s to the negative 1, or 1 over m times s. And oh, sorry, if I've been saying m and s the whole time, s is seconds and m is molarity still. So it's 1 over a equals the constant times time plus 1 over a sub 0. And one thing I need to mention, a sub 0 in these problems will be the initial molarity of the reaction, and then a itself will be the final molarity of the reaction. So now let's do this problem. A reaction of A products follow a first order kinetics with a constant of 1.56 times 10 to the negative 4 seconds to the negative 1. How long will it take for the concentration of A to drop from 0.8 molarity to 0.125 molarity? What is the concentration of A that remains after 2 minutes? How long will it take the reaction to be 40% completed? Now, we're going to leave out this part right here because I think after I'm done explaining these, then I think you guys should work on these on your own. So let's start with the first question. How long will it take for the concentration of A to drop from 0.8 molarity to 1.25 molarity? So now we have our equation that we looked at just a minute ago, and our final molarity is a natural log of 0.125 molarity. That's in the right spot. And then the K constant that they gave us, negative 1.56 times 10 to the negative 4 seconds, negative 1, and then times time plus the natural log of 0.8 molarity. So then you just do the natural logs in your calculator. It will be negative 2.08, and then this will turn into a negative as well, so it'll be minus 0.223, and then you will want to add this to this side, which will make negative 1.857. And since your remaining unit is seconds, you're going to want to display your time in seconds, which you'll do here with some division, or basically multiplication with dimensional analysis, as I like to do. So it'll be negative 1.857 times seconds over negative 1.56 times 10 to the negative 4, and that will give you 11,904 seconds. Now let's do the second one. What is the concentration of A that remains after 2 minutes? Now the value that they gave us is seconds, so we're going to want to convert minutes into seconds, which I did here. It's 120 seconds. So then we use the same equation that we were using before, except now we're looking for the final molarity value after 2 minutes. So we're going to need to solve for that. So first we multiply the time, 1.56 times 10 to the negative 4 times 120. I need to do this real quick. I decided not to write all of it out. It'll be negative 0.01872, and then plus the natural log, of 0.8, which we still have up here. So then when we add those together, we get negative 0.242. Then to solve for natural log, we do Euler's number, or E, to the power of natural log of A, and then on the other side, Euler's number to the power of this number, negative 0.242, and then the E and the natural log will cancel each other out. Oops, I should probably use the red for that, as I've been doing. And it'll just be A, and then it'll be E to the negative 0.242, and then your final value, when you put E to the negative 0.242 in your calculator, your final value of A, or the molar concentration after 2 minutes, 0.785 molarity. So finally, we'll be doing the final part of the question, which is written out right here, but the question itself reads, how long will it take the reaction to be 40% completed? Now to do that, you just take the initial amount, 0.8 molarity, and then multiply it by 60%, or 0.6, because 40% is gone. That gives you a final value of 0.48 molarity. So then you plug those things into the equation, and you're finding time again here like we did the first time. We get the same value, different value here, and you add it to here, and that makes it negative 0.511 times seconds over your constant, and then that will give you 3,276 seconds. So finally, we'll be doing something a bit different than we've been doing. A reaction of A products follows second order kinetics. If it takes 14.25 minutes for the concentration of A to go from 0.768 molarity to 0.455 molarity, how long will it take for the concentration of A that remains to be 0.645? Now we're not going to be doing this last part because you already know how to do that, or you should, according to this little procedure here in these equations, but we will instead do something that we haven't done yet. which is finding the K value from these values given. Now first we'll be using our second order kinetics equation, because it says it's a second order kinetics, and that will be 1 over the final molarity value equals the constant, which we're trying to find here, times time plus 1 over the initial molarity value. So then we plug in our numbers, so it goes from 0.768 to 0.455, so 0.455 is our final value, and then we have K, what we're trying to find, times minutes. It doesn't say to answer in seconds anywhere here, so I'm not going to convert. So 14.25 minutes times K, and then plus 1 over the initial molarity value, 0.768. Then you do some division here. 1 over these numbers will give these. And to even it out, you'll subtract 2.198 molarity to the -1. You'll subtract this 1.302 molarity to the -1 from that. So that'll basically give you 0.896 molarity to the -1, or 0.896 over molarity. And then you'll want to divide that. I didn't write this all out, but this will be equal to K right here. So you'll want to divide your number for the molarities by the number for the minutes, 1 over 14.25 minutes as division rather than multiplication. Then that will give you 6.29 times 10 to the -2, molarity to the -1, minutes to the -1, or 1 over molarity times minutes. So if we look up here for second order kinetics, we have our time value. Doesn't always have to be seconds, by the way. I've seen ones that are, days, weeks, minutes, hours. So it doesn't always have to be seconds. So minutes to the -1, or sorry, not minutes. Got time on the brain. But molarity to the -1, seconds to the -1. That looks about correct if we go down here. So this is a completed problem. So thank you all for watching. I'm sorry that this is somewhat last minute, but hopefully it'll be a good preparation for whatever kinetics tests, quizzes, or homework you might have. So again, thank you so much for watching. Soon we'll be moving on to our next unit, equilibrium, and then it will be summertime where we go into review mode. So stay tuned for that.